Casey's getting on a bit, like a lot of us, and it's international travel's difficult. So, but I do have a plug, because Guy is retired, but of course, like most academics, that doesn't mean he stops doing stuff. And what he's actually done is just finished a book, a new book, on Markov modulated Brownian motion, the Matrix-Analytic perspective, and this has come out with Springer, and that's what he says. So that's obviously not a Springer endorsed ad, because it hasn't got the right colors and anything, but it's one that Guy just asked me to mention, and I certainly would like to just remind you. Not everyone knows Guy. I know quite a few people here do. I was thinking about him overnight, and I think he's probably got a claim to have made the biggest contribution to the field of matrix-analytic methods since Marcel. And he's certainly done an awful amount. So now I have to work out how to get out of here. You know, escape. Escape doesn't work. No, stop sharing. Okay. And Control-Alt-Tab should work, shouldn't it? Escape tab. Yeah, sorry. I thought I had that under control, but obviously not. I'm working on, you know, reducing the success of the conference. Thank you. Bravo. Okay, so I'm not got a very long talk. It's about analysis of skip-free Markov additive processes. It's joint work with Guy, and it's also, I'm going to talk a fair bit about some recent work that both of us have done with Evgeny Ivanov's. So let's see if this works. And it's about these things called Levy processes. Now, I know there are people here who are going to know about these things. I suspect there are people here who don't. I've known about them for quite a long time, but I must admit, they were sort of like a remote thing. I never tried to work on them, didn't have much intuition about them. But I do want to make a plug, because I actually think they're the most general object where it's natural to apply matrix-analytic methods. So matrix-analytic methods started out with block-structured Markov chains, and various, we've had fluid models, we've had Markov modulated Brownian motion, as you've just seen. The most general thing that we should be applying matrix-analytic methods to are Levy processes. And why is that? Well, I've taken this definition from Ciprianu. So a process, a Levy process, if it's got almost surely right continuous sample paths, that just means it's a stochastic process in the sense we think about it. It starts at 0 with probability 1. But the most important things are these ones. For any times s and t, x of t minus x of s has got the same distribution as x of t minus s. So the evolution just depends on the difference. And what's more, it's stationary in the sense it doesn't matter where you start, where the xs is. And it's also independent of the process up to time s. So a Levy process is the most general process on the real line that has stationary independent increments. So, what do we know about them? Well, there's many sorts, but we're going to talk about one-sided Levy processes today. And these things can have jumps, but the jumps can only be in the positive direction. So, the important result about Levy processes is that it's all about, I think, I was sitting there during Ivo's talk, and it was all about Laplace transforms. And we've seen them a lot today. In the conference, we've seen inversion, talks about inverting. As I get more and more long in the tooth and older, I actually think Laplace transforms are the most important thing. And in fact, I think when you're teaching a second-year probability course and you talk about density functions, distribution functions, probably the best thing to summarize a random variable is its Laplace transform, Laplace-Selches transform, or characteristic function. It's transform. It's the most natural thing. And I think just for young people, thinking of working in the transform domain, I think is a really important technique, which we've seen examples of. And that's what the guys who work on Levy processes do. So this thing is the expected value of e to the alpha x of t. So it's really the moment generating function of the process at time t. And the important result is that that has a form of e to the t times some coefficient. And that coefficient depends on alpha. So if you take the log of this, then it basically says that the log of the moment generating function is linear in t. And the coefficient is this thing called psi of alpha, and that's called the Laplace exponent. And the famous result, it's a Levy-Kenshin formula, provides a general expression for the Laplace exponent of Levy processes. And it's basically got three different terms. So you've got to remember over here, this is the moment generating function, and we're multiplying this thing by t. So if you multiply this by t, this is t sigma squared over 2 times alpha squared. And if you remember when you're teaching your probability courses, that's the moment generating function of a normal random variable with variance sigma squared times t. So it's basically saying that you can have a Levy process. This is a Brownian motion, right? Because it's got a normally distributed state at time t. And its variance is sigma squared. This is a linear drift at rate a. And this complicated looking thing is essentially a compound Poisson process. It's not quite that, because essentially if you integrate over this thing called a Levy measure, if it's finite, then you can say that's a Poisson process with that rate. And then this basically gives the distribution of the jumps. But technically a Levy process, you can have this measure being infinite, which is sort of like saying you've got a Poisson process with infinite rate, but the jumps are arbitrarily small, and don't worry about the technical details of that. For modeling purposes, you can basically say that the general process with stationary independent increments is a composition of a Brownian motion, a linear drift, and a compound Poisson process, modulo that technicality about infinite measures. So they're really important processes. There's a massive number of applications that use those things. Okay, so that's scalars. But of course, we're a Matrix-Analytic Methods conference. We look at stuff on, that have general two-dimensional state spaces. So just a little bit of notation. This thing's a matrix, right? E something colon j of t. It's an n by n matrix with the ij center. I is the initial phase, and j, oh sorry, that wasn't meant to happen. And j is the final phase. So this is the expected value of whatever you're taking expected value of, multiplied by the indicator that we're in phase j at time t, and we're in phase I at time 0. And you can do that with the probability matrix, and I'm just going to use delta V for a diagonal matrix with the V on the diagonal. Okay, so what's a Markov additive process? Roughly speaking, well, it's a bivariate Markov process. So we have an x, which is like the x I had before. We have a phase j. X lives on the real numbers. J is a finite bunch of phases, which we might as well number 1 to n, and we call them level and phase. So that's not going to be a surprise to anyone here. And essentially, this is a phase version of the Levy stationary independent increments property. It pretty much says that's true, but conditional on the phase. Right? So that's the sort of thing we see all the time. So the increments of the level process are governed by the phase process J, and J evolves as an irreducible continuous time Markov chain. It's got some transition rate matrix Q. So what a map actually is a Markov modulated Levy process. It evolves as a Levy process, xi, well, j equals I. Something else can happen, and Azam's going to relate to this because she talked about switching Markovian point processes. You can also have jumps when you have a switch in the phase space. So you can, well, the phase is sitting in I, it has its own I-dependent Levy process, but when a jump happens, when a jump in the Markov chain between phases happens, you can also have a jump in the level. So that's what a Markov additive process is. And it's not going to surprise anyone that there's a matrix version of the Levy exponent, of the Laplace exponent. Okay, and this is it. And essentially you have a diagonal matrix with all the individual Laplace exponents of the various phases. And you've got this extra thing here that deals with the possibility that you can have jumps whenever the underlying phase-type Markov chain jumps. Okay, does anyone want to ask any questions about this? Because they're the objects I'm talking about. So, oh, it's Hadamard, you know, just element-wise multiplication. Q times, yeah.
Just wondering, this model with this multi-server system with patient customers.
I think they all can. I'm going to say a little bit about models here. Yeah, I mean, you haven't got a Brownian component, I don't think, or maybe, I don't know if you have, but maybe, yeah. But yeah, you have drifts. Yeah. This is a general process that can have Brownian motion, it can have drift, and it can have jumps. And the jumps occur at a Poisson process, but the jumps can be arbitrary size, so it's a compound Poisson process. Okay. So there's a matrix version of the Levy-Khinchin formula. So we've got, remember this is my notation for matrix, we've got an expression for the expected value of e to the alpha x of t, which is a matrix exponential because f of alpha is a matrix here. So it's exactly the same. It's a matrix version of the Levy-Khinchin formula. And this is something that's a result, we know about, you know, drift of say, a quasi-birth and death process or an MG1 type train. They are that drift to infinity. This case, I haven't got a boundary at 0, so it drifts to infinity, drifts to minus infinity. There is the driftless case, right? So this is a result that holds in general. There's some constant such the limit as t approaches infinity of x of t over t equals u, almost surely, for every initial state. And if mu is greater than 0, that means x of t drifts to infinity. If mu is less than 0, it drifts to minus infinity. If mu is equals 0, in other words, that's a driftless case, then in fact, the lim sup of x of t approaches infinity and the lim inf of x of t approaches minus infinity. Just think of a standard Brownian motion, right? That has drift 0. It can go arbitrarily high and arbitrarily low. So Evgeny, Guy and I, we've had this paper lying around for literally 10 years. It's one of these unfortunate papers of mine that's been referenced even before it's been published. So, but we looked at what we called lattice and non-lattice Markov additive processes and tried to put together the Matrix-Analytic tradition with the tradition of people who work on Levy processes. And so what do we mean by lattice process? Well, lattice process, we just take our level set not to be R, to be Z. So that means it can't have any Brownian motion. It can't have any linear drift. It can only have jumps, and the jumps have to be of size 1. But all those, that's a perfectly reasonable Markov additive process. It falls within the class we're talking about. What it actually is, of course, is a continuous time Markov chain of MG1 type. And we know about those things. There is one slight thing. I said it was one-sided, which we couldn't have negative jumps. When we make a process lattice, it has to be able to go downwards. So we allow jumps of size -1, right? Which is what exactly makes it an MG1 type process. So your MG1 type Markov chain does fit in this framework. And, you know, as I said here, this is familiar, but some of the things we do can provide insight for the Markov additive community, and some of the things they do can provide insight for us. And I could give the rest of this talk just about MG1 type processes, but I thought I'd be a bit ambitious and not do that. I'm going to give the talk in the case of non-lattice processes, which are the ones that have continuous level sets. So the important thing is tail of y is the first time that the level equals y. All right, I'm going to use that notation a lot. And here's the result. This is basically the analog of our matrix G. But you've got to remember we're doing this on a continuum. So this is a matrix, remember, and it's the matrix of the phase at time that the process first hits level -x, so it's going downwards. Remember, the only way it can go downwards is continuously. Jumps can go up, can only continuously go downwards. So it's like an MG1 type process. So the important thing from our point of view is a matrix G. Because it's continuous, we don't have a matrix G, which is a transition matrix of how the phases change when you go from one level down to the one below it. It's actually a continuous process in space. And in fact, you can show that the transition probabilities of going from level 0 to level -x have the form e to the gx for some transition rate matrix G. So there's a transition rate matrix which governs going downwards. So that's like a continuous version of the familiar matrix G that we have in MG1 type processes. And guess what? It satisfies a matrix equation. Now, we're used to it being a matrix polynomial equation for MG1 type processes. But in this, what you actually do is you put in G for alpha in the matrix Levy exponent and put the whole thing equal to 0. So there's a matrix equation that anyone who likes numerical analysis and stuff can go and work on. Now, there's something that the guys who work on Levy processes worry about, and Brownian motions and things like that, that we usually don't. I mean, this is sort of a concept that's fairly standard for us, but not so much for them. And that's this concept. They call it a local time. We sometimes call it an occupation time. So what it really is, think of this as if you start in phase J of level 0, this is the amount of time you spent in level X in the interval 0t. Now, because we've got things like Brownian motions and stuff, you can't actually add, Brownian motion spends 0 time at any point. It moves around infinitely, you know, has unbounded variation. So what it actually is, and this might be a sloppy way of thinking, but I think of this, it's like a spatial density of position. So if you then put them all in a matrix and you let t be infinity, then you can have the expected value of the local time at level x. And we call this a matrix hx. And this one, h of 0, is the expected time spent at level 0 in time 0 to infinity, given you start at level 0. Now that's it. You can write that quite easily in an MG1 type Markov chain. It's a bit more analytical if you're doing it in a general process. So one of the things that we showed is that this matrix H of x has got finite entries for all x, unless x of j is no recurrent, unless the drift is 0. And essentially, that's because the process is going to drift to infinity, or it's going to drift to n minus infinity, it's not going to hang around in any given level for an infinite amount of time. Okay? So that's true. That makes sort of intuitive sense. Furthermore, we can show it's non-singular. But if the drift is 0, then this matrix of expected occupation times is every entry, and under appropriate irreducibility assumptions, which I'm not going to state, but every entry is infinite. So it's either all finite and non-singular, or it's all infinite. Okay, what about R? R is a lot harder in this context, because if you go back to the proofs of R, you always talk about things like the last time you leave a level before you go to a higher level. And that's not something you can define with a Brownian motion. So, but there are ways to do it. But so the way to define R, and it's like we've seen in previous talks, R is a matrix of ratios of expected occupation times. And that's the right way to think of R. So, you have to be pretty careful to define what these are. So we start at level 0 in some phase, and theta star is the first time the phase changes. So it hangs around in a phase for a while. And then we define theta dash as the first time after that you return to level 0. And you have to do it this way because of this idea that you've got a Brownian motion at level 0. It returns to level 0 instantaneously. So you can't do the sort of normal things we're used to. You actually have to wait some time before you return to level 0. Otherwise, it's not a proper return. It does my head in thinking about Brownian motion, because if you look at a graph, it does go down and come back, right? So there's a difference between coming back after some time and coming back instantaneously, but they're really hard to tear apart mathematically. And so then we just define the matrix R to be something that, that is a ratio of the expected time spent in phase J at level minus X, given we start in phase I of level 0, up to this time of first return, divided by the expected time we stay in phase I of level 0 before we have a first jump of the phase. So if you like, it's what we've seen before. It's a ratio of expected times at the next level to expected times at the current level. So this is another result that we showed. This thing also has a matrix exponential form. And it satisfies the same equation, but we multiply on the left. So again, you can stick it in the Laplace exponent, put it equal to 0. Really beautiful little theorem. If the drift is not 0, yeah.
Is that a xt?
Yes. Yeah, sorry, it should be there. Yeah. Thanks. Yeah. If the drift is not 0, so if it's either drifting to infinity or drifting to minus infinity, then there's this beautiful relationship between the e to the gx, the probability transition going down from 0 to minus x, and the local time then spent, or staying at level 0 and having this matrix of ratios of local times. And the proof is not quite as trivial as this, but the intuition behind it is that both the left and right-hand sides are expressions for the expected local time at minus x, given you start at level 0. So this is really saying we start at level 0, first thing you do if you're going to count the amount of time that you're going to spend at minus x that you've got to get there. And the matrix that tells you how you get there is either the gx, what phases you are in when you get there, and then you've got a matrix of the, then you're effectively at level 0 because of the spatial homogeneity. And so you then just say, well, what's the amount of time I've spent, local time at level 0, given I'm starting there. And over this side, it's a bit more complicated, but you basically say this is like the amount of time you've got at level 0, and this is the amount of ratios of the amount of time you spend x lower. So that's true if u is not equal to 0. But if u equals 0, both those h's, both sides of that relationship are infinite. So it's true, but it's useless. So just to step back, I've got a couple of minutes, I hope. At the last conference, Guy did give a talk about QBDs and other processes with zero drift, and explained how most of the algorithms we got don't work as well. So the Newt's original linearly convergent algorithm, or Guy's original linear convergent algorithm, are only linear convergent if mu is non-zero. If mu is equal to 0, they're sublinear. The logarithm reduction algorithm, cyclic reduction algorithm, which we've heard about, converge quadratically if mu is non-zero, but if mu is equal to 0, they don't. They converge linearly. So things are always worse when mu is 0, and there are even some situations where we are missing equations when mu equals 0 because matrices are singular and things like this. So we'd really like to work out what's going on. And we've got some idea. And it's really about, instead of trying to count local time up to infinity, you should count local time up to a certain random time. So what can we say? Well, this is one thing we can say, and maybe we need to still keep working to get this out. We really say, well, tau of minus x, you start at 0. Tau of minus x is the first time you go to level minus x. And then eta is the first time you go, the first time after that, you go back to 0. Now, that's going to happen with probability 1 in a process with mu equals 0, because you're going to visit 0 infinitely often. So we've got an expression for the amount of time spent at level, the local time spent, expected local time spent at minus x before eta. And you can again think of it as we say before, it's we can go downwards. We've got to get down to level minus x, and having got there because of the spatial homogeneity, it's sort of like counting the local time but starting at 0 before we get back up plus x to get, which would get us back to 0. And on the other side, we've got a similar thing. So this is a relationship which doesn't look anywhere as neat as that one, but in fact, it does even hold for the processes of mu not equal to 0, and possibly this is the more fundamental relationship, even though it doesn't look quite as neat. And that's all I've got. Thanks, everybody.